As a reminder of the 4 power series that you must know so that you can manipulate, okay, they're present here on your note card. You can manipulate the series above to find new series as long as you're centered at x equals 0 by doing these 3 things right here. So let's look at some examples. Number 1. All right, manipulating one of the known series is probably the best way to go, best approach for this one, if we're supposed to find the first 4 non-zero terms and the general term for this function. What I mean is you really don't want to go through and find 3, 4, 5 derivatives of this function right here and evaluate it at 0. I mean, I will if I have to, but if I've memorized the e to the x series, then why not manipulate that, okay, to come up with, you know, the first 4 non-zero terms and the general term for this. Okay. Again, you could do it by hand if you wanted to, do all the derivatives like we did on the previous 2 note cards, but it might be easy just to do some substitutions. Okay. All right, what I noticed is that I can pull 6 out. And like I say, this function is equal to 6 times the summation of, and I'm going back up to the e to the x series. That's one way, working with the generic summation formula. Okay, and I see that it is x to the n over n factorial. So everywhere that I see x, I'm going to replace it with, I'm subbing in this new exponent. So I'm subbing in negative x over 3 to the n. Okay, and of course I could do some cleanup on that, but now what I'm going to do is I'm going to notice, okay, that that's just actually inserting negative x divided by 3 in every x in the different terms of above. Also multiplying by 6. So look at the first term of e to the x, it's just 1, so I'm going to multiply by 6. And the next term is x, so it's going to be 6 times, not what x is, but, excuse me, negative x over 3. And the next term is x squared divided by 2, factorial. That'd be negative x divided by 3 squared. How many terms? I need the first 4, so I've got 3. Plus dot, 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 plus this one right here. I guess I need to wrap it around. So did I need to write this line? No, certainly not. Just looks nice. Okay, you can clean it up or not if you want to at this point. And oh, it appears I need to put a 6 in here too, don't I? I need to multiply that by 6. I think previously I'd left it all factored out, but I do need a 6 in there. So I think that all looks in order. Right, first 4 non-zero terms and then the general term for the Taylor series. And unless there's a need for me to clean it up, maybe if I'm doing a ratio test, I would clean it up a little bit, but at this point I'm just going to leave it. All right, looks like in example 2, we're going to manipulate the sine x parent series. All right, write a power series, Maclaurin series, and the general term for sine of 2x. So just look up above, find the sine x parent series. Everywhere you see x, replace it with 2x. So I'm going to say f of x is equal to sine of 2x. And actually on this one, I'm just going to get started with the terms. The first term of the parent series is x, so I'm going to replace that with 2x, and that's how we're going to start. Okay, for the sine series, it's odd exponents, alternating signs. So this is going to be 2x quantity cubed. Oh, it's interesting. It didn't tell us how many terms to write. So we'll do at least 3. So 1, 2, 3. I'll do one more. We'll do 4. Then I'm going to wrap it down here, wrap it around down here and say plus dot dot dot. All right, and looking at the general term there, just everywhere I see x, replace it with 2x. So that goes to 2n plus 1. And actually, this is 2n plus 1 down here, factorial. And then we have the alternating situation, negative 1 to the n. Right. Again, if there's a purpose, a later purpose for what you need to do here, you can clean that up. I mean, if you're trying to use the ratio test or whatever, I'd probably do a little cleanup. But for the requested question, I'm done. Everywhere I saw x, I just replaced it with 2x in the parent series. All right, we're going to find the first three non-zero terms in the general term of the Taylor polynomial for the given g function, centered at x equals 0. All right. Okay, it just looks like where cosine x squared is, I'm going to use the parent series for cosine x. And so looking up ahead, looking up above, seeing that cosine x's parent series is given, everywhere I see x, I'm going to replace it with the x squared. So maintaining the structure of the g of x function, I'm going to have to create a very large fraction because what I'm going to be doing is putting in three non-zero terms to replace this right here with the general term as well, and keeping the minus 1 and the x in the denominator. So it's going to get kind of crowded. All right, looking at cosine x parent series, I start off with the 1, so no adjustment there, minus x squared. So I'm going to insert x for x. I'm going to insert x squared for x, but I'm also going to have to square that. 2 factorial. Plus x squared to the 4th over 4 factorial. And those would be the first three non-zero terms, so I'm actually done there. Plus dot 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 plus going to the general term. Oh my goodness. Replacing x with x squared. Raised to the 2n over 2n factorial plus dot dot dot. Okay, keeps going, and then I need to jump back in. All of this was just for cosine x squared, and then I've got a minus 1, and then I still had it divide by x. I'm done. I can do some cleanup, but I'm actually, in fact, done with the requested information. Likely, though, we'd have to do some cleanup for a later question. Notice the ones would cancel. Okay. And if I did a little bit of cleanup here, I think there was something else that we had to do with this problem. So it became necessary for the students to do a little cleanup here. See if I can get this all back here. All right, that first term is going to be, it looks like x to the 4th over 2 factorial. Whew. And I think it was a negative, actually. I'll look back at what's missing there. Yep, it was. Plus this next term would be x to the 8th. I know it's not leaving your paper, so look at your paper. Over 4 factorial minus x to the 12th over 6 factorial. Ooh, I see a pattern there. Plus dot dot dot. Looks like x to the 4n over 2n factorial. Okay, and then plus dot dot dot. And notice that actually we're dividing by x, so that actually just reduces these exponents by 1 as well. So taking it a step further, dividing this x to the 1st out of every term up here in the numerator that does have a variable x in it. I end up with negative x cubed over 2 factorial plus x to the 7th over 4 factorial minus x to the 11th over 6 factorial. Ugh, I turn my head and it's gone. Oh, goodness. X to the 4n minus 1 all over 2n factorial. Again, you would have been finished up here, but it's probably better to go ahead and simplify it, at least in this context when the problem started out something like this. The thinking would be for us to simplify it. And plus, when you get down to this point, it's easy to find a derivative. That would be a likely question. What is g prime? You know, what is g double prime? And so it's easier to work with terms like this when they're cleaned up. All right, Cliff Note 18 next. The main topic of this note card is manipulating series, but doing so by differentiating or integrating a known series. For example 1, we're given this 4th degree function, and you're probably missing some parentheses, so I tried to recreate the 4th degree polynomial down here. All right, except I can't seem to get the 4 exponent to stick there, but I think you guys can see that down here when you write it, you're going to get the 4 exponent here. All right, our objective on this problem is to write the 2nd degree Taylor polynomial for the derivative about 4 and use it to approximate f prime of 4.3. So just take what they gave you and differentiate it. Right, the constant goes to 0, and then thinking about what was there and using the chain rule, I'm going to get negative 3. Plus, I believe that was an exponent of 2. 2 times 5 is 10. Quantity x minus 4. Derivative of the inside is just 1. Oh, my goodness. Minus, and I guess this next one would be 6. Quantity x minus 4 squared. Okay, and then, of course, to finish, we're going to evaluate at 4.3. Everywhere you see x, replace it with 4.3. 4.3, so 4 minus 4.3 is negative 0.3. Oh, I'm sorry, 4.3 plugged in. This was, hello, this was 4.3 plugged in for x, minus 4 is 0.3, positive 0.3. Minus 6 times 4.3 minus 4 is 0.3 squared. So not too bad without a calculator. This would be negative 3 plus 3 minus 6 times 0.09. I squared the 0.3. So I'm left just to multiply right here. These will cancel. Negative 0.54. I'm going to try something different just because that Word document is being crazy. I'm going to be just on a plain sheet of paper, but just go ahead and put this in the space right underneath 1b. All right, it asks us to write a 4th degree Taylor polynomial for this function g defined by this integral. So that's suggesting to us that go back up to our 4th degree Taylor polynomial and replace f of t, okay, with that polynomial with some adjustments. Now, a couple things to point out here. Look at this lower limit of 4. All right, that 4 is there because that's the center that we're working with. If the center we were working with was 2, the integral would start with that center. All right, so we're going to have to integrate the terms of the previously given Taylor polynomial. So let me get it set up. Okay, notice that our integrand is in terms of t, which means that in my 4th degree Taylor polynomial, I'm going to replace every x with t. We don't typically have the same variables in our limit positions as we do in our integrand. So t. All right, I'm going to stop right here because it asks me to create the 4th degree, and when I integrate right here, I'm going to get the 4th degree. All right, so I'm going to integrate here. It's going to go back to 7t. But be on the lookout. When you integrate backwards, where center is 4, so let's make that adjustment. It's really 7 quantity t minus 4. All right, let's go ahead and integrate here. Use substitution is not necessary, but it's going to be this quantity right here divided by 2 plus, and right here, increase the exponent, divide by the new exponent. All right, and then we have to evaluate from 4 to x. All right, so everywhere we see x, or sorry, everywhere we see t, we're going to replace it with x. I just simplified this one. Okay, minus, remember everywhere we see t, we're going to replace it with 4. So that's just going to create a bunch of zeros there. So it's really just minus 0. Yep, so that's it for that one right there, just integrating. Okay, let's look at number 2. I'm going to stay on this Word document. So in the space provided on your note card, we're finding the first 4 terms in the general term for the Maclaurin series for f prime of x. Okay, so I'm just going to differentiate 4 terms and the general term. So f prime of x. When I differentiate here, I'm going to get 4x. When I differentiate here, I'm going to get 8x. I see bringing that in front, it's going to cancel here, leaving you 8x squared. Okay, and then I'm going to start to notice the pattern. It looks like this is a geometric series, so it looks like I'm multiplying by 2x to produce the next term. So remember, it's S just for 4 terms, the first 4 terms. I need one more. So your options were to either generate another term up here, or just notice that it is geometric. Okay, and even if you were to generate the next term, we should get 16x cubed plus dot 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 plus, and then right here, okay, notice what happens when you differentiate. You bring the n plus 1, it's with respect to x, bring the n plus 1 in front, cancels with the n plus 1 here, so plus 2x, okay, to the n when I reduce the exponent by 1. Continuing to differentiate with the chain rule. Okay, so and the derivative of the inside function is 2. So we do also have to multiply by 2. I'm not sure if that conversation was disjointed. Honestly, I had a distraction, so hopefully that was flowing nicely. And finding this derivative right here requires the chain rule. So we have the first 4 terms and the general term right here. You can put the 2 up front if you wanted to, but otherwise you're done. Let's look at example 3. All right, part A says on 3, find the power series for f prime of x. Okay, if you wanted to, you could generate a few terms, starting with n equals 1 here, 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 and here. You could generate a few terms, but it wasn't really specific about how many terms. It's just saying find a power series, so I'm just going to work with the general term. So I'm going to differentiate this general term right here, and if necessary, make an adjustment on my summation notation, my index right here. Finding the derivative with respect to x. Pull the n in front. Notice it cancels with this n down here, so I'm left with quantity x minus 5 to the n minus 1. The n was pulled in front when I differentiate. It cancels with this one down here, leaving me to have 5n. Okay, and notice there's no chain rule necessary because the derivative of x minus 5 is just 1. So this is it. Okay, other than let's make an adjustment now, okay, on, if we need to, on the index. Okay, and here's where it'd be helpful to generate a few terms back up here. If n is 1, then we're going to have quantity x minus 5 over 5. Maybe generate another term, then you're going to have minus, because if n is 2, that's odd, and it's going to be quantity x minus 5 squared over 2 times 5 squared, plus blah, 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 blah. Okay, if I differentiated this term right here, the first term down here that I should have is going to be 1/5 x. Pardon me, this is going to be this derivative would just be 1/5. Put it down here. Okay, and then finding this derivative right here would result in the 2's canceling and then reducing that exponent to 1 minus x minus 5 to the first over 5 squared plus blah, 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 blah. Okay, how do we get 1/5? Okay, what should we begin n with? Well, I need a positive term, so I guess I'm not going to adjust to 2. I think I'm going to stay with an exponent of 1, because if n is 1, I'm going to get quantity x minus 5 to the 0 power, which is just 1. If n is 1, I get 5 in the denominator. If n is 1, I do get a positive 1. So I'm going to stay with the index of 1. So you could always generate a few terms and go back and test it. This is what we're looking for here, though, the derivative of this power series. Okay, so part B has us integrate. All right, notice we have no limits. That's nice. That's why we're staying with an x. I know I'm going to have a constant of integration, so I'm going to start with that. C plus I'll leave this blank for the moment. Let me integrate this with respect to x. So increase the exponent by 1, divide by the new exponent. So this whole part of the problem is going to stay. Increase to n plus 1, divide by n plus 1, keeping everything else. I don't really see much of a cleanup, so I guess I'm just going to leave it like that. To figure out what index I should start with, 0, 1, etc. You can always go back to the terms that you generated and integrate if you wanted to. So this is going to be, if I looked at that, it's 1/5 quantity x minus 5. If I were to integrate that, that exponent is going to increase to 2, and I'm going to divide by the new exponent. So I guess I would leave it with the 5 down here. So x minus 5 squared times a 2. All right, so how would I, need to begin to start this so that I did get this right here? Well, looks like I would need to start with a 1. That would make this exponent even, hence the positive coefficient. If n is 1, that's a square, and that's what I need here. If n is 1 here, I get the 2 in the denominator. If n is 1 here, that's great. If n is 1 here, I get that exponent. So it all looks like it works out well that I should be starting with n equals 1. So we can integrate, we can differentiate, integrate general terms. just pay attention to the indexing, and the way to kind of nail that down is to generate a few terms and see if you can create them with a certain starting end value here in your derivative or your antiderivative. Sorry for the length. It's just one of those topics that you can't really condense it too much. Thanks for hanging in there.